I'm going to be going over the Big M method introduced in Week 5 Monday's lesson. The example problem they gave us was Bevco manufactures an orange-flavored soft drink called Orange by combining orange soda and orange juice. Each ounce of orange soda contains 0.5 ounces of sugar and 1 milligram of vitamin C. Each ounce of orange soda or of orange juice contains 0.25 ounces of sugar and 3 milligrams of vitamin C. It costs Bevco 2 cents to produce an ounce of orange soda and 3 cents to produce an ounce of orange juice. Bevco's marketing department has decided that each 10-ounce bottle of orange must contain at least 20 milligrams of vitamin C and at most 4 ounces of sugar. We're going to use linear programming to determine how Bevco can meet the marketing department's requirements at minimum cost. So by letting x1 equal the number of ounces of orange soda in a bottle of orange, and x2 being the number of ounces of orange juice in a bottle of orange, what we're going to do is minimize the cost used to create this soda. So we're given this setup LP and we were asked to put in constraints. And we got the constraints from the given problem. So the first constraint is the sugar constraint. So we look at the sugar constraint in the orange soda and orange juice. So the orange soda contains 0.5 ounces of sugar and the orange juice contains 0.25 ounces of sugar. So we're going to have 1/2 x1, which is our orange soda, and 1/4 x2, which is our orange juice. And at the very end, it says that each 10-ounce bottle of orange must contain at least 20 milligrams of vitamin C and at most 4 ounces of sugar. So if it's at most 4 ounces, we want this constraint to be less than or equal to 4. Then we look at the vitamin C constraint and determine it similarly. We look for the amount of vitamin C in the orange soda and the vitamin C in the orange juice. So that would be 1 and 3, which we put into the equation accordingly. And it says at the very end that the orange must contain at least 20 milligrams of vitamin C. So if we're talking about at least, that means we need x1 plus 3x2 to be greater than or equal to 20, which is our milligrams. Our last constraint is the 10-ounce bottle of orange, because we're making a 10-ounce bottle. We want x1 plus x2 to be equal to 10. So x1 is going to be our amount of orange soda and our x2 is going to be the orange juice. Okay. So then we want to put this LP into the correct form that we can put it into a table or a tableau. So we do this the same way that we've been doing it in previous lessons before week 5. Whenever we have a less than or equal to constraint, we can add a slack variable and then make that equation equal to whatever's on the right hand side. Whenever we have a greater than or equal to equation, inequality, that's what it is. Whenever we have a greater than or equal to inequality, we can subtract an excess variable and make the right hand side equal to whatever it is. And then we have our last part of the equation, x1 plus x2 is equal to 10. That's just left as is for now, for what we've been doing, basically. And right here, we're just saying that S1 needs to be greater than or equal to 0, and E1 has to be, or E2, sorry, has to be greater than or equal to 0. And then we can put that in our tableau, including the minimization problem right here. The optimal function, optimization function. So then we see that if we look at our table right now, our S1 is equal to 4. And it could be a basic and feasible variable for row 0 or for row 1. So then it asks, will any value of E2 work as a basic variable in row 2? So if we look at E2, would we be able to, it's asking, would we be able to solve E2 equal to 20? So if we have -1 equal to 20, if E2 is a, if we make this a pivot row, if this turns into a 1, so multiply the whole row by -1, we're left with E2 is equal to -20. But we know from up here that our E2 must be greater than or equal to 0. So that's why we can't necessarily have this kind of row in there already. And is there a readily apparent basic variable row for row 3? And if we look here in row 3, we don't have one because these all have numbers above them. Even though there's ones right here, there's numbers above them, and it's not so easy to make it a pivot row. And this is already a pivot column, and this is nearly a pivot column if we multiplied it by -1, but we see that we can't do that in the previous problem. So we need to basically change the table up by adding in different variables. So it says to remedy this problem, we will invent a basic feasible variable for each constraint that needs one. Because these variables are created by us and are not really decision variables, we call them artificial variables. So with the addition of artificial variables for row 2 and row 3, which were our problem rows before, we have this new setup of equations where A2 and A3 are our artificial variables. And now we have the following, that Z is equal to 0, S1 is equal to 4, because if we look at S1, it is equal to 4. If we're looking strictly at the table, then A2 is equal to 20. Excuse me. And A3 is equal to 10, which is what we want. The only problem with the LP as written is that the optimal solution is Z equals 0, S1 equals 4, A3 equals 10, and X1 equals X2 equals 0. So as of right now, what we have is already optimal, and it's not the optimal solution for our original LP. This problem arose because one of the artificial variables is still basic in the optimal solution. So we need to tweak our objective function so that the artificial variables end up being 0 in the optimal solution. So how should we go about changing that so that way the table is optimal or rectified? Since this is a minimization problem, we want to make the artificial variables cost more than the decision variables. This is because when we make the artificial variables bigger, it makes them, it puts them so far away from the actual answer that it virtually doesn't count them as an answer, but it helps rectify our table. So thus the simplex algorithm will choose the decision variables over our made artificial variables. So we make our new objective function, Z is equal to 2x1, 2x1 plus 3x2 plus 100a2 plus 100a3. And where we get the name, the big M equation, it comes from putting in 100 or a large number where those artificial variables are, which is what is said in the next part of the document. We decided on 100 basically randomly. It just has to be a large number. If 100 was not enough to force A2 and A3 out of the basic variables, we could try 1,000 or 10,000. But in general, we denote these arbitrary choice of a big cost as M. So then we have our tableau formed, but it's not well formed. So we put in those artificial variables, but as you can see, these aren't yet pivot rows. We have these artificial variables in here kind of blocking us from having these as pivot rows. So what we do is we need to zero out these columns, meaning we need to get rid of the negative 100 in the A2 row, or A2 column, and the negative 100 in the A3 column. So we do that by multiplying 100 to row 2, and then adding it to row 0, and then multiplying row 3 by 100 and adding it to row 0. In the first step, we took care of A2 in initial tableau 1. We took care of the negative 100 in A2, and then in initial tableau 2, we took care of the negative 100 in A3. So now that we have a feasible tableau, it is rectified now. We want to go through our simplex algorithm like normal. So since we're doing a minimization problem, we want to look for the largest most positive in row 0, which is 397, and then do the ratio test for the right-hand side. So we take 4 over, or whatever's in B, and divide that by whatever is in our largest most positive column. So we have 4 over 0.25, or 4 over 1/4, which is 16. We have 20 over 3, which is 6, and we have 10 over 1, which is 10. And we're looking for the smallest most positive. So we get 6 point something. I forget exactly what that goes to. Let me do that real quick. Is 6.6 repeating. And then we turn this into a pivot by making this value 1 and zeroing out this column. So we want this number here, and this number here to be 0, which is done in this iteration. As you can see, our column x2 row 2 is a 1, that's our pivot, and the rest of the column is zeroed out. So now again, we look for the largest most positive, which is 198 over 3. And then we want to do the ratio test, which it turns out that 10 over 3 divided by 2 over 3 is the smallest most positive. And then again, we want that to be a pivot column, so we turn that into 1 and zero out the rest of the rows using our row operations like we've been doing, and scanning row 0 for any positives, in excluding B, the B column. We don't have any more positives except for our Z, which is we leave the Z there. So this is the final iteration. This is optimal, and it's saying that Z is going to be 25 when x1 is equal to 5, x2 is equal to 5, and s1 is equal to 1/4. And you can go through this on Torah, which I have open, and I have already set up the table. So this is from the first iteration once the Tableau is optimized. Or sorry, once the Tableau is rectified. So we're looking for the largest most positive. We can click there. And using the ratio test, 20/3 was the smallest most positive. So we click there and hit next iteration. 65.67 was the largest most positive in this one. And we had, what was it? No, sorry. Which was it? Let me just hit next iteration. Oh, I thought I clicked that one. Okay. So this was our determined to be smallest most positive by the ratio test. And then it gives us our final solution in iteration 3 on here, saying that z is equal to 25 when x2 is 5, x1 is 5, and sx4, which was our s1, I believe, is 0.25. Right? Yes, our s1 was 0.25. And then we have the week 5 Monday assignment. So that covers all the notes, but we still have the homework assignment. So we want to use the big M method to solve this LP. It's minimize z equals 4x1 plus 4x2 plus x3, where the constraints are x1 plus x2 plus x3 is less than or equal to 2, 2x1 plus x2 is greater than or equal to 3, and 2x1 plus x2 plus 3x3 is greater than or equal to 3. And our non-negativity constraint is being used as well. And so we look at this and we know that we need to use the big M method because we have these greater than or equal to signs. What is it? Week 5 Wednesdays assignment, there's another method of finding the solution to these optimization problems. It's, I believe, the two-phase method, but for now we're just learning the big M method. So what we want to do is turn these into our turn them into equations that are will properly fit into the simplex Tableau. And again, how we do that is if there's a less than or equal to sign, it's going to be a plus S1. So as you can see here in row 1, we have plus S1. And then when it's greater than or equal to, we'll have a minus E with a subscript number, so E2 or E3, but then we'll have a plus A2 or A3. And if you're wondering why we're using S1 in this one, and then E2 and A2 in this row, and E3 and A3 in this row, it's because we keep the number of the row aligned with the number of the subscript, just so that way it's a little bit easier to see which falls with what constraint. So we know that S1 will be with constraint 1, and E2 and E3 will be, E2 and A2 will be with constraint 2, and E3 and A3 will be with constraint 3. Okay, so it says enter this LP into Torah and solve it using the big M methods iteration on there, or plug it into Sage and solve it by creating a sufficiently large M value. As you can see here, I did it out on on my paper, which I'm going to zoom out, and if you want to pause and look at the work there, you can, but I am going to go over how to plug it into Torah with you. So, oh, that might not work. Let me make this a little bit smaller and see if that'll work. Oh boy. There we go. Nope. Okay, well, I have it on paper next to me, so if you have the paper with you, you can pull it up next to you so that way you can see where we're getting the numbers, since it doesn't seem like I'm going to be able to show both at the same time. What we're going to do is go to main menu, linear programming, and we want to enter a new problem. So we go to the input screen, and let's title this problem week 5 Monday assignment. And it's asking for the number of variables. Since we have x1, x2, and x3, we have 3 variables, and we have 3 constraints, not including the non-negativity constraint. So we'll name our first variable x1, second variable x2, and third variable x3. And in this problem, we are asked to minimize. So if it's already on maximize, just click it and it'll change to minimize. We're minimizing the problem 4x1 plus 4x2 plus x3. So you type in a 4, and then a 1. And this is just matching up with the problem. So if you're not sure where I'm getting these numbers, it's still back from this problem that we had up. Our first constraint, we have 1x1 plus 1x2 plus 1x3 is less than or equal to 2. So need to change this part. But in our second constraint, we have 2x1 plus 1x2 plus 0x3, and we have greater than or equal to 3. So on your keyboard, you should be able to see a greater to sign. You just hit that and it should fill it in. You won't have to hit the equals, but if the equal isn't there, you can just hit the equal on the keyboard. And then we are greater than or equal to 3. The third constraint, we have 2x1 plus 1x2 plus 3x3, and it's greater than or equal to 3. And then I've been leaving the lower bound and upper bound as 0. This lower bound is basically saying that x1 needs to be at least 0, x2 needs to be at least 0, x3 needs to be at least 0. So that's basically our non-negativity constraint. With our upper bound, we want to be able to find the minimized problem. So no matter, like, even though we want a minimized problem, it may go up to 100. We don't know. So we leave that at infinity and leave that as unrestrained. So then once you have all this inputted, you hit solve menu. We're going to save the data real quick. And then you want to go to solve problem, algebraic, iterations, and it's going to give you different ways you can solve this. If you hit final solution, it's going to come back and tell you that you're not able to do that since it does require a special sort of tableau to be able to solve it, since we have to use the big M method or two-phase method. If it were just a regular LP like that we've been doing in previous weeks, you would be able to just hit final solution. But it's also good to use iterations. That way you can see what, like step by step, where we're getting each part. So we're going to go to iterations and then M method. And then it says enter the value of M. I'm going to do 1,000 this time just to be sure that our M is big enough, but I believe 100 works with this problem. So then go to output format screen. And then again, output screen. And then we're looking at the iterations once the Tableau is rectified. So this has it in the form to where our A's are already going to be pivot rows. So it already figures that out for us. We just need to optimize it. So since we're minimizing, we look for the largest, most positive in row 0. Click that, and you'll know you got the right one when it turns green. If you click the wrong one, it's going to give you a little error message. Let's see. So in the next row, or in this column, I believe it's, so we have a tie here actually. We have 3/2 and 3/2. In Tora, you're just going to want to choose the very first one. It won't let you choose the second one. It'll say when there's a tie, you must choose the first one to appear or something similar. And then once we've clicked both of those, hit next iteration, and it'll bring up the next iteration when that row is turned into a pivot. So then again, looking at where the most positive is in row 0, we have 2,999. And then ratio test, we have 0.5/1, 1.5/0, which is 0, and 1.5/0, which is, you're not able to do that, and 0/3, which is 0, so that should be the least most positive, but okay, yeah, I wasn't sure if Tora counted that as the least most positive, but it is. So then we'll go to the next iteration. And it says that our iteration 3 is optimal. So this means that this is our final iteration. This is our optimized Tableau in iteration 3. So looking at it, we find that Z is equal to 6 when X1 is equal to 1.5, X3 is equal to 0, and SX6 is equal to 0.5. And looking back at my notes, I believe I have that Z is equal to 6 when X1 is equal to 3/2, which is 1.5, X2 is equal to 0, X3 is equal to 0, and S1 is equal to 0.5. So that is week 5 Monday's assignment. If you have any questions, feel free to leave them in the comments below, and I will respond as long as I know the answer. And I hope this helped.